Today we're going to get a 2015 PAT paper and doing question 20. So question 20 is about the energy in an atom. So in a hydrogen atom, we're told that the energy levels are given by this equation, En equals minus R over n squared, for some constant R and positive integer n. We're told the atom is excited to a state where n equals 10 and then allowed to de-excite, emitting light before settling to the level n equals 1. We are told to find A, the shortest, and B, the longest wavelength of light emitted, and C, the number of emission lines. So let's start by writing down our fundamental equations when it comes to considering quantum stuff, quantum equations and the behaviour of atoms. Well, we have that our speed of light, c, is equal to the frequency of the photon times its wavelength. We also know that the energy of a photon is equal to Planck's constant times the frequency. So let's consider part A. Part A asks us to find the shortest wavelength of light that is emitted from this atom. Well, let's think about this. If the wavelength is short, then the frequency must go up because the speed of light is a constant. All photons have the speed of light. So if the frequency goes, the lambda goes down, then F must increase. So if F is high, then we clearly see from this equation that we're going to have a large energy. So this photon is going to have a high amount of energy. So to find the shortest wavelength, we're looking for the photon emitted with the largest amount of energy. Well, this is clearly going to correspond from a change from the highest energy state to the lowest energy state, as the photon carries away the energy of the atom. So if we find a transition of an electron from n equals 10 down to the lowest energy state, n equals 1, the difference between the energies will give us the energy of the photon of light emitted, and then that will allow us to find the shortest wavelength. So let's do that. Well, the change in energy is going to be equal to the energy at the n equals 10 state subtracted the n equals 1 state. Well, that's equal to minus r over 10 squared, 100, minus, well, at 1 it's just r over 1 squared, or r. Well, this is equal to minus r over 100 plus r, which is equal to minus 99r over 100. So we know that this photon emitted will have energy of 99r over 100. So we know from here that E equals hf. And we're told we can leave things in terms of Planck's constant. So we have that minus 99r, in this case the energy of the photon is just 99r. 99r over 100 must be equal to Planck's constant times its frequency. And this tells us that the frequency of the photon is going to be equal to 99r over 100h. We then use our next equation here, C equals F lambda, to tell us that lambda equals to the speed of the wave, speed of light, over the frequency. Well, that's just C over 99r over 100h, which tells us that lambda equals 100hc over 99r, and that'll be our shortest wavelength. Now let's do the same thing for our longest wavelength. Well, it's going to be exactly the same idea, but in reverse. So the longest wavelength will be the lowest frequency, which will be the photon of the least energy. So we're looking for the smallest transition in energy. Well, this is going to be clearly from n equals 10 down to n equals 9. So let's work this out. So the change in energy will be E10 minus E9, which is minus r over 100 minus r over 9 squared 81. Well, this is equal to r over 81 minus r over 100. So we put the denominator as 8,100, timesing this on timesing top and bottom here by 100 and top and bottom here by 81. So that gives us 100r minus 81r over 8,100. Well, that's going to be equal to 19r over 8,100. Plugging this in again, we're going to get that our frequency, as before, will be equal to 19r over 8100h. And this tells us that lambda is going to be equal to 8100hc over 19r. And that's going to be our longest wavelength of light emitted. Now on to the final part of the question. This asks us to find the maximum number of emission lines, so the number of emission lines that are possible? How many can be emitted as the atom de-excites? Well, let's think about this by drawing on a few of the energy states. We know they converge as n tends towards infinity, so they're going to be slightly closer together at the top. So let's draw n equals 10, n equals 9, n equals 8, and n equals 7, and label those on. So this is our n equals 10 state, n equals 9, n equals 8, and n equals 7. So let's think about the transitions that can be made from n equals 10. Well, it can clearly move down to n equals 9, it can move down to n equals 8, move down to n equals 7. In fact, it can move down to any of the ones below 10. So we have 9 possible options. The transition from 9 can go to 8, to 7, to 6, and so on down to 1. So that gives us 8. If you spot the pattern here, 8 can go to 7, it can go to 6, and so on and so forth. So we get 7, and so on. So in fact, our total number is going to be 9, add 8, add 7, add 1. And when you evaluate this sum, this gives us 45. So our answer is 45 possible emission lines.